Right. Hello. Enjoyed yourselves? Good 2 days? Yeah, and it's Friday. How intelligent is that, to finish a conference on a Friday? I wish more conferences had that intelligence, because now you have Friday night and the weekend. You can either wash away your Java-based troubles over a beer tonight, or you can let it all sink in. So I'm going to give you a closing keynote here, and then there's a little close after that, some additional farewells from the organizers. And there are a lot of different ways that keynotes can go. Sometimes you have the kind of the big, inspirational, big picture keynotes. Sometimes you have the product placements. One of the great things about being an independent consultant and trainer is that I have nothing to sell except myself. I am the product, okay? So there's no version numbers or anything like that. I'm not going to tell you about databases that you should or should not buy or anything like that. But it's not customary to have lots of code in a keynote. So I'm going to give you lots of code. But I do want you to walk away feeling inspired. So what we're going to do is, if this works, I'm going to use the force. Okay, apparently that doesn't work. The battery's died. Oh, no. No, I know the problem. There we go. It's all about focus. I would like to talk about cool code. Based on a very simple observation that we have a history in software development, and sometimes we don't realize that we have a history effectively of literature. There's a lot of code that has been written. Not all of it's good, but there's an awful lot of code we can learn from. And sometimes we learn things that are not useful to us on a day-to-day basis. We learn things that make us interested and excited, or that's just kind of cool. That's what I'm interested in. So, any more product placement from me? No, but I'm going to focus on the one on the right. 97 Things Every Programmer Should Know, a book that I edited, and I led the project. It's an open source book, so you can actually find the original material online, and it's a crowdsourced book. It's not my thoughts, it's many people's thoughts. And as a project, it was quite fun, but perhaps one of the most interesting things that I discovered in terms of quality was the Japanese translation. I love this. It's fantastic. I can't read Japanese, but the production quality of the book. If you're going to kill trees to create books, all books should be created like this. I was told in advance by the editor of the Japanese versions are always so much nicer. The quality of the paper, they change the templates, they take a lot of care over it. This book has a dust cover on it. It's a wonderful thing to behold. Now, what I want to do here is translate it back into English. I'm afraid my Polish translation skills are not very good. Translate it back into English and borrow something that I mentioned in the intro and the preface to the book. There is an art, craft, and science to programming that extends far beyond the program. The act of programming marries the discrete world of computers with the fluid world of human affairs. Programmers mediate between the negotiated and uncertain truths of business and the crisp, uncompromising domain of bits and bytes and higher constructed types. That is one of the things that makes programming both fun and challenging. That you deal between these different, you move between these two very different worlds, the world of high precision, unforgiving ones and zeros, types that have a very definite opinion of how you use them, and then the world of people who are slightly less rational, well, not rational at all, but are interesting and move in a very different way. But I've mentioned there, I've evoked things. I've mentioned art, craft, and science. We could go further. We can talk engineering. We can talk architecture. We can talk other design disciplines and other disciplines of creativity. But am I stretching this? Do we have art? Well, yes. Sometimes it's not always what we intend. That's art. I like to think of it as an ad hoc installation piece in Copenhagen Airport. It's a sort of a brave and confounding expression It's a deconstruction of a program. I particularly like the shade of blue. I like the vertical alignment. I think that's a very pleasing proportion. I was very disappointed that on my return flight through Copenhagen, they'd apparently fixed this and replaced it with a rather boring advertisement. So sometimes we have art that is accidental. But there is a deeper point here. I'm going to borrow from Karianne Berg, who wrote the entry in 97 Things on read code. She observes that we programmers are weird creatures. You know, I would have accepted the article just on that sentence. We love writing code, but when it comes to reading it, we usually shy away. After all, writing code is so much more fun, and reading code is hard, sometimes almost impossible. Reading other people's code is particularly hard. Not necessarily because other people's code is bad, but because they probably think and solve problems in a different way. But did you ever consider that this could improve your own style? And this is the observation. This is why it is interesting to look at other people's code. Normally people think, well, I read a lot of code. You know, our system is huge. I read lots of our code base every day, so I already read code. No, that's not what I'm talking about. I'm not talking about the code that you already work on. I'm talking about code, reading code for its own sake. In the same way that other design disciplines often look at existing designs and design history almost for its own sake, but also to see what has been done. It gives you a broader vocabulary and a broader outlook on what you can do. It gives you ideas, it enriches your, well, actually, it does everything. It makes things exciting. But you do have to be careful about the code you look at. Examples of code that I don't think we should be spending our time looking at. This. Let me just focus your attention. This is not the kind of thing that we wish to be interested in and focus our efforts on. Sure, we read stuff like this every day, but that's not going to improve your ability to express yourself, except perhaps as a negative example. We have examples like this. Now, this is a very interesting piece of code for a number of reasons. This is actually Ada code. But apparently the correct way of describing this style is Ada-tran. It is Ada written with a very strong Fortran accent. I have to admit, the first time I saw this code, I thought, why have they written in Fortran? Because they're Fortran programmers. They've been given this language that is apparently far more expressive and far more powerful, and they've chosen to write Fortran in it. And they've not done it very well. And if we look up, we can see all kinds of stuff. We can see duplication. We see this kind of this if-else-if structure recurring. We love the names. I mean, how meaningful are these names, you know? And this 16 and 32, that refers to bit size, right? And this is just really a mess. And then we've got these magic numbers. And we can't even make up our mind what base we want them in. Oh, let's have it in decimal. No, change my mind. Let's have it in hexadecimal. I mean, if you're going to have magic numbers, at least use the same magic spell each time. And so this is kind of all over the place. Perhaps what is more interesting is that this was originally the code, and this is the bit that's interesting, that launched this. 4th of June, 1996. About 39 seconds into flight, we had this. This was the maiden flight of Ariane 5. It's been estimated to have cost, in all of its consequences, something like $300 million US. That's a very expensive firework. It's a very inefficient mechanism for scattering satellite parts over the forests of French Guiana. We can learn a lot from this code. We can learn a lot from its assumptions. It was reused code from Ariane 4, but they forgot to test it using Ariane 5's flight profile. It was not actually necessary code. It served no purpose. So next time somebody says, oh, we don't need to remove dead code, show them this. Okay? This code was not necessary in Ariane 5. It actually handled a part of the flight control, the initial guidance for the initial launch sequence that disabled 40 seconds into flight. This control had been moved to ground control. It was no longer on the rocket. So it was redundant code. And they forgot to retest it with certain parameters. In fact, we can be very specific about this. You see, what actually happened is they did a little rounding. They cast a 64-bit floating point number to a 16-bit integer. Now, there's two things here that are worth pointing out. First of all, if you're listening to what I'm saying, you're thinking, well, hang on, he's just said 64-bit. But I don't see the number 64 anywhere. I see 32 and I see 16, but I don't see 64. I actually had somebody email me after I gave a talk that included these slides and said, I think you're wrong about the 64-bit. No, I read the original report. I'm right about it, but what we have here is one of those other lessons about naming. Choose good names. It was originally 32-bit, but then they changed the underlying type. But there's too much administrative overhead, because this is a safety-critical process. You have to sign off on changing names of variables. So we'll change the type, but we won't change the name. Oh, that's very safe. Now, I don't know, I should be feeling worried because I'm flying home tonight, and one of the flights is on an Airbus A321. Airbuses have a lot of code, and a lot of it's in Ada. So we have that observation. We also noticed that actually there was a little overflow issue, is that Ada has a very strong idea about overflow. It doesn't like it. If you work in a language like C, which is very relaxed and very laissez-faire about these things, Ariane 5 would have gone into orbit had it been programmed in C. It would have said, oh, that's interesting, you overflowed. Well, that's of no interest to me, and just let the garbage data accumulate until it was shut down. But if you use a proper language like Ada, you blow it up. This is an interesting example. It's an example of what is technically known, now I've been using the word rocket and exploding, but actually there's a technical term, RUD. This is another, for those of you, yeah? Rapid unscheduled disassembly. Next time you want to describe something as exploding, you say, anybody could say explosion. Yeah, and you've seen the logo for GeeCON, right? Yeah, it says Java explosion. No. Java RUD. Okay, that's where we want to be going with this stuff. So this is not the code we want to look at either. We want to look at code that is cool. It's fashionably attractive, or it's impressive, or it's excellent. Sometimes we use the word cool to express acceptance or agreement. Cool. Sometimes we describe it, we use it, I know my older boy uses it a lot, it's like, yeah, cool. You know, you've got to put the emphasis in there. Sometimes you use it just to fill the space. If everything goes quiet. Cool. Sometimes it's about a complete lack of respect for something. You describe something as cool when it's just insane and ridiculous. So that's where we're going to go. And there's a bunch of definitions for code. One of which is a collection of writings, which is also interesting. Now, let's have a look at one of my favorite ever pieces of code. I've not sat there going through this. This was described in a blog. I put the link to the blog on the top right, the bottom right, sorry, the right-hand side. This was once described as the greatest program ever written. To understand why, you need to understand the context. It's 1983. This is Z80 assembler. And this was targeted at the Sinclair ZX81, a home computer that kind of changed the relationship between people and computers, and along with a number of other computers in the early 80s, certainly in Britain helped to launch a whole generation of programmers, because suddenly they had affordable equipment that they could just plug into their television and mess about with code. But the ZX81 had a very, very limited memory, 1K. So let's just remind ourselves that's 1,024 bytes. And some of that's used by the runtime. This program, written by a chap called David Horn, was is a chess program that fits in 1K of memory. This program has basic AI. The computer can play you. It knows the rules of chess. It can display on the screen. And it recognizes a win or a draw. And importantly, it's not done in 1024 bytes because the runtime takes space. It's done in 672 bytes. That's 4.8 tweets. Okay? I want you to think, can I describe the rules of chess in 4.8 tweets? No. So somebody here said that's impossible. Exactly. That's what makes this so cool. That's why this is cool. It's one of those, it's just like, you can't do that. Apparently, we can. Okay? So it's challenging. It's exciting. Going further back in history, we also see other interesting examples. This is the part of the source code for the Apollo 11 lunar lander, the Eagle. And this is available on Google Code. There's a nice little entry on Lambda the Ultimate, which I've included in a link there you can find. This is the, basically this is the handwritten assembler. There was a compiler, let's see, what's it called? Mac, it's Mac code, MIT Algebraic Compiler. So there was a high-level language, you wrote the code in the high-level language, and then you compiled it by hand, manually. That's why the assembler has good comments. Okay? It's compiled down. So those of you who are sitting there so used to incremental compilation in the background, and sometimes you think it's a bit slow, I want you to think about what this means. Okay? This is really slow. And so this was compiled, and it was for a 36-bit computer with about 20K of memory, if I remember correctly, and a clock speed that you measure in kilohertz, not megahertz or gigahertz. And this actually, apparently, you can put people on the moon with that. These days, we don't seem to be able to put people on the moon. We've got much better technology, but we clearly don't have what it takes. We're confused by our own technology. But there's some great bits in this piece of code. Let me just highlight here what this says. You might not be able to see it. Temporary, I hope, hope, hope. Temporary, I hope, hope, hope. It's one of those things about comments. Always be careful with your comments. Sometimes you reveal more than you meant to. The interesting thing is that this code, the code for the Apollo 11 lander also had a bug in it. And the reason we never discovered that never caused a problem is because it was cancelled out by another bug. Yeah, the bugs were sympathetic. They cancelled each other out. So Apollo 11 landed with this. Apollo 12 landed with this. They fixed it for Apollo 13. Yeah. So, yeah, little issues occasionally, you know. They didn't really get to test it till 14. Then we have other little examples of code. This is a piece of code from 1999. What's lovely about this is it's perfectly self-contained. Nice bit of C code. It's from a book by Kernighan and Pike. And it's called The Practice of Programming. And I remember reading this book, just going through. There's some lovely stuff in that book. It's a very restrained, very understated book. It's a very classic piece of Kernighan writing. And they presented a little version of grep. And I remember turning the page, it's just like, no, wait a minute, that was it. You just presented grep on one page. Now, it's a subset of grep. It's not going to compete with a full-blown grep, but it turns out that actually expresses a fairly common subset of what people need and use. And it has some very nice execution properties. It's also a fairly convincing example of how to use mutual recursion. And this is really impressive. Now, I've loved this piece of code for ages, but there was a wonderful example in the book Beautiful Code, where Brian Kernighan was asked to, was one of the people that was asked to select a piece of code that they found beautiful in some way. And Brian Kernighan chose this. This was done by Rob Pike. He knocked this one up in an afternoon. But there's a lot here. If you go through it, you really realize that this is very minimal code, and it really expresses every single idea necessary. There's not much you can do to improve this. We have other examples of code that are not necessarily quite as clever or intricate, but have had a profound effect. This is one of the earlier versions of JUnit 3. I've been trying to get out of Kent Beck a version of JUnit 2, but this is kind of the bit where everything happens. This is the kind of the part of the kind of nano kernel in the heart of JUnit. It's not very big. It's not particularly profound or intricate code, and yet a certain simplicity to this has led to a shift in people's perception of what it means to test their code, the availability of testing frameworks and things like that. It was just one of many things, the basic simplicity that allowed a larger thing to happen. While we're on the subject of testing, this isn't a piece of code. Well, it relates to a piece of code. One of the little languages I quite like, used to have a particular fondness for, is awk, which is a little language-based, a scripting language based on pattern matching. It's in many ways, it got displaced by Perl, which is nowhere near as elegant, although it is slightly more comprehensive. But awk is quite a neat little thing. It has a very particular and very interesting model of execution. There was an interview with Alfred Aho, who's the A in awk, Aho, Weinberger, Kernighan. Would you do anything differently in the development of awk, looking back? Well, one of the things I would have done differently is instituting rigorous testing as we started to develop the language. We initially created awk as a throwaway language, so we didn't do rigorous quality control as part of our initial implementation. How many systems start their life like this? Yeah, it's just a throwaway. And suddenly, before you know it, it's the most important thing that your company's shipping. I mentioned to you earlier there was a person who wrote a CAD system in awk. Now, I have to say, if you know anything about awk, this is nothing short of either impressive or insane. I used to really like awk. I don't think I wrote anything longer than 150 or 200 lines in any single script. To write a CAD system in awk it's like running it's like running a marathon on one leg, you know. You'd be amazed if somebody could do it, but you might wonder why they did it. The reason he initially came to see me was to report a bug in the awk compiler. He was very testy with me, saying I had wasted 3 weeks of his life. Oh. When somebody walks into your office and say, you have wasted 3 weeks of my life, you expect that to be followed up with, and I demand your soul, the blood of your firstborn son, and the lives of all your parents, okay? That's a fairly major thing. So I huddled with Brian Kernighan after this. We agreed we really need to do something differently in terms of quality control. So we instituted a rigorous regression test for all these features. Any of the three of us who put in a new feature into the language from then on first had to write a test for the new feature. Does this sound familiar? Test first programming. They just didn't popularize it. They weren't responsible for making it a big thing. They just thought that this was a logical way of doing it, to confirm that a feature did not already exist and then write to that. Now, it doesn't have the finesse or the approach that we now recognize as a test-driven approach, but this is the 1970s. There's a lot that's changed. And it's surprising to find things back then. In fact, if we scratch the surface, we can actually find a lot of modern agile thinking going further back. This is a quote that I was directed at a couple of years ago by Glenn Vanderberg, by Alan Perlis, the winner, if I recall correctly, the first winner of the Turing Award. I'd like to read 3 sentences to close this issue. A software system can best be designed if the testing is interlaced with the designing instead of being used after the design. Okay, that sounds pretty good. A simulation which matches the requirements contains the control which organizes the design of the system. Not obvious what that means, but if you've used mock objects, that's what we're looking at. Through successive repetitions of this process of interlaced testing and design, the model ultimately becomes the software system itself. I think the key of this approach has been suggested. There is no such question as testing things after the fact. This is really interesting. What makes it more interesting is that it was 1968, and it's the software engineering conference, the first NATO software engineering conference. It turns out, apparently, in the late 60s, there were people who actually had a clue and actually knew some good ideas and were prepared to explore them. They didn't have necessarily the confidence and maturity and the scale of software development we have now. But certainly, when people sort of say, oh, well, it was the 1960s, that was the waterfall process. Well, no, it wasn't. Clearly, that's not a universal. And what you have is that something happened in the 1970s to make this a less normal or reasonable approach. I've had various theories thrown at me about the 1970s. Some people say that it was disco. Some people say that it was flared trousers. I don't know. But only recently, in the last 2 decades, have we recovered this territory and actually started to see, you know what, this is not unreasonable. And in all of this, we have an idea that perhaps sometimes the simplest approach, or something that's too simple to be real or reasonable, is a good way of doing things. This is a nice piece of code. Now, just to clarify, I've just said that it's a nice piece of code and it's in Perl. So, I mean, obviously, I'm a little bit, I've obviously had a very long week. No, this is a nice piece of code. It's the top and tail of about 200 lines of Perl. This is the first wiki. This code is by Ward Cunningham. And although we're going to point out a couple of things, he's got some commented out code, no indentation, but the abstraction is surprisingly elegant, because this is the main body. It's here. It's very, very simple. The intervening 150 lines has simply been setting up different procedures. And then we have this very elegant main chunk. It's very, very small. And yet this describes everything you need to know about a wiki. Very, very simple. It's one of those things that had anybody looked at it, they'd have said, that will never come to anything. Yeah? It's one of the few things that I can actually impress my older son with. My older son is now 10. He is decreasingly impressed by anything his parents do, by definition. But if I say, Ward Cunningham, and he says, who's he? The guy who invented the wiki. Oh, wow. Do you know him, Dad? Yes, I've had him in my car as well. I've driven him. I've drunk with him, and it's like, oh wow, that's pretty cool. Doesn't matter anybody else I've ever met. That's real as far as he's concerned. But it all started in 200 lines of Perl. Then we have other little interesting things. This is a piece of code by Erwin Unruh, who worked, in fact, I think he still works for Siemens. The date of this is 1994. This is C++, and it is the origin of C++ template metaprogramming. Now, if you're not sure about what C++ templates are, I want you to think of Java generics, and then forget it, because this stuff is actually proper generics. This is generic in the way that Java generics aren't. In fact, it turns out that, and this is what this proves, it turns out that C++ templates are Turing complete, which means that if there's anything you can calculate in principle, it can be done with the template mechanism. What do I mean by this? Well, if we look at all of that, look at the bottom here. This program does not compile. So what use is a program that doesn't compile? Its error messages give you the first few prime numbers. Yeah, so that's pretty cool. Yeah, it's one of those accidental discoveries. It's just like, oh, and I remember when this happened, immediately it was around the office, okay, do we have a compiler that does templates? Yes. Okay, let's reproduce this. Right, now, we've got prime numbers. What about Fibonacci? What about, it's insane. And it launched a whole segment of job-preserving activities for C++ programmers. Because when you write C++ template metaprograms, nobody will ever be able to replace you. But even now, we have a lot of fun. We can see this. I stumbled across this the other week. This lovely example based on a template metaprogramming library. So a little tighter, a little smaller, a little more expressive. It's actually a functional program. It turns out that because you can have no side effects at compile time, it's a pure functional program. Does anybody know the game FizzBuzz? FizzBuzz is a game. It's also a a kata that people often use to practice on. You count the numbers. It's also a drinking game. Now, it's interesting. If you Google FizzBuzz, you will find some sites say that it is a child's game, and some sites say it is a drinking game. I don't see the difference. The idea is you count 1, 2. If a number is divisible by 3, you say fizz. Okay, 1, 2, fizz, 4. If a number is divisible by 5, you say buzz. 4, buzz, fizz, 7, etc. When you get them both divisible by 3 and 5, then it's fizz buzz. Okay, 13, 14, fizz buzz. Okay, if you get it wrong, drink. But not if you're a child, okay? So this program does this, and it has the same kind of consequence. It's compilation message, compilation error here, 1, 2, fizz, 4, buzz, fizz, 1, 7, 8, fizz, buzz, 11, fizz. Fantastic. So the error message actually is, it's practically intelligent. This is the other meaning of the Turing test. Okay? Fantastic stuff. Absolutely crazy. Then you have things like Gary Bernhardt's base library for Ruby. This is utterly insane. The base library, if you inherit from base, it automatically gives you all of the methods in the system. You inherit every single method in the system, which I think for Ruby on Rails is 6,000 or 7,000. So if you ever wanted to have all of that functionality available, you just inherit base and you can do anything. I'm not entirely sure it's meaningful, but that's slightly odd. That's fun. That's ridiculous. Then we have stuff that is interesting from a very different point of view, profound in another way. This is my copy of the Lisp 1.5 Programmer's Manual. It's put together at MIT in the early 60s. I mean, Lisp was born in the late 50s, but the Programmer's Manual came out in the early 60s. John McCarthy and others put this together. It's a wonderful document. You can find the PDF online, but as somebody interested in the history of this stuff, I thought I'd get a physical copy of it. Really interesting as a book as well. It's really well written, and it gives you a complete guide, not simply to the Lisp language as it was seen as then. It gives you a guide to how to construct it. If you sat there reading the book and with a compiler in front of you, you can recreate Lisp in its original vision. It's absolutely fantastic. There's enough detail there to do it. Now, Lisp was quite profound in a number of ways, one of which, there's some interesting minor observations. 1.5, John McCarthy always regarded the whole parenthesis stuff, all the round brackets. He regarded that as an intermediate step. He didn't think that that was necessary. And so Lisp 2 was to have none of this. It turns out that was actually quite an important feature. It never got beyond 1.5 in that sense. But there is something in here that's really quite interesting and quite profound. And I'll show you the sort of a scheme version of it. This comes from the Structure and Interpretation of Computer Programs. This is the scheme version is slightly tidier than the original Lisp version, but the originally came from Lisp. The idea is that the eval function here, the eval function is Lisp. It evaluates an expression with an environment, a context object, if you will, of variables. And it interprets the expression as a data structure and then figures out what to do. Does it evaluate itself? Is it a variable? Is it quoted? If so, then do that. Is it an assignment? Is it a definition? Is it an if statement? Is it a lambda? In which case, perform a binding and re-execute, and so on, and so on, and so on. So in other words, this is Lisp written in Lisp, or Scheme written in Scheme. Which is a really profound idea. There's a very interesting recursive idea that we live with in software. The idea that many compilers, in fact, it's now seen as a mark of a complete language. Can the language be written in itself and then ported? Can you cross-compile? Well, the first time you come across cross-compilation, it's something to get your head around, but you realize there's a certain benefit as well as a certain elegance to it. We have this recursion in the sense of seeing that Linux is built on Linux, is hosted on Linux. JUnit tests JUnit, and so on. We have this kind of cyclic structure. Now, this has a number of interesting consequences, one of which is that the reason that many programming languages in the 1970s were created, a lot of the AI languages, for example, a lot of the AI languages came about because somebody wanted to solve a problem. And often they were based on Lisp. So normally somebody would say, well, I want to solve this, or I want to understand something. I would like to explore this. So what I'll do is, I won't solve it. I'll create a language to help me. Yeah? This is the ultimate procrastination, the ultimate work avoidance scheme. We have a very challenging problem. Let's create a tool. And so you get this whole wave of Lisp-like languages, and Scheme was one of these. The problem Scheme was designed to solve, and it was Sussman and Steele who were focused on this, particularly Guy Steele, was understanding Carl Hewitt's actor model of computation, which came about in the early 70s. And having read Carl Hewitt's early papers, I kind of understand where Guy Steele was coming from, because they said, we have no idea what he's doing. We don't know what it means. We think it's really profound, but we're not sure. So Scheme was created to help understand and experiment with the ideas of actor-based computation. And in Scheme, they originally had two interesting constructs. One of them, the lambda, the other, an alpha. And the alpha was an actor object. And it was the simplicity of code. Often people underestimate why simple, small code is important. They often say, oh, no. These small code examples you're showing, that's all very well, but we have real code at work. It's thousands and thousands of lines long. You know, that's real code. So this stuff doesn't apply. Well, it turns out it does for a number of reasons, and we'll come to that. But there's a benefit here that you can see. You can hold this code in your head. And it turns out that when they wrote out something very like this, and they wrote out the alpha expression, they realized that the code for the lambda and the alpha was identical, except for the word alpha and lambda. And at that moment, there was a great blinding flash of light, and Guy Steele realized, wait a minute, alpha objects are the same as lambda functions. They are the same concept, just from a different side. So you have this unification. This is one of the reasons, in some senses, that Alan Kay, inventor of Smalltalk 80, once described the eval function as being a little bit like Maxwell's equations for computer science. And we see sometimes people take this and take it a step further. This is Lispy. It's a kind of a basic Lisp written in Python, written by Peter Norvig, Director of Research at Google. What I love about this is that in 90 lines, so there's the eval. You can see very, very similar structure. You know, very, very simple, express it in this way. And there's the main REPL, the read eval prompt loop. I've missed out a little bit of code, but he gets the whole thing in 90 lines. Lisp in 90 lines. He said he tried it in Java. It took him about 1,400 lines. Little bit of a difference there. So, I said earlier on we should treat software and coding as fun. We often forget the fun. And the fun is in being able to play. Play is a very underestimated, undervalued commodity. Sometimes people like solving puzzles. They like creating things to some kind of challenge. This is the winner of the 1989 International Obfuscated C Coding Contest. It won the best layout category. You know what's really funny about it? It calculates E. Now, you see, that is funny, because that's the whole point. You have to be quite a geek to find that funny, and you do. Because it has the classic ingredients of humor. It creates a situation, and then there is a conflict, there is a jarring juxtaposition. It's like, hang on, that's not pi, it's actually e. All of that, everything about it says pi, but it's e. That's quite funny. Now, if you want to calculate pi, you need this one, which is the winner of the 1988 Best Layout category. This program calculates pi to 2 decimal places, so 3.14. It calculates pi by measuring its own surface area. So what we see here is, again, that idea of self-reference, a program doing something with itself. One of the most impressive examples is this one from Yusuke Endo 2 years ago. It's an example of a quine, or a multi-quine, a program that will produce itself as its output. But what this does when it's executed is this is Ruby code, and it will produce a Ruby program with the world rotated through 45 degrees. And if you execute that, it produces a program further rotated by 45 degrees. And if you want to run it and put in your own choice of degrees, you can do so. If you want to rotate it 1 degree at a time, it will do that. On the page on which he announced it, there are some really amazing comments, but my favorite is the 3rd or 4th down, which is, do you accept worshippers? This is a magnificent piece of code, and you know what? I have no idea why you'd want to do this at work unless you are really bored. It won't promote the direct productivity of anything, but the fact that somebody has done this not only shows that it's possible, but it actually gets you sort of thinking, how did they do that? It makes you understand the language. It makes you want to understand the language. I have to say, for the International Obfuscated C Coding Contest, learning about the IOCCC over 20 years ago, I learned an awful lot of C techniques because it relies on really knowing the language and the dark corners. In other words, you're challenged, and it's quite fun. So occasionally we come across other little pieces that are slightly surprising. Now, with any luck, I've got that. Where is it? There we go. So I've got that code there. Got that. I'm running extended desktop, so I can't see what I'm doing. So, yeah, there's the code. Now, this is really interesting code because it came out at the beginning of last year. Nobody knows who was responsible for it because it was posted anonymously. And given that we're talking about pi, what's really cool about it is, well, just watch. What does it do? It sorts. This is called sleep sort. Now, for those of you who know anything about sorting algorithms, what's the complexity of this algorithm? It's an ON algorithm. Okay, it has some other performance properties that are not so great. But hey, this is quite cool. And funnily enough, there is stuff you can learn from this approach to distributed processing. So yeah, that's slightly crazy. Slightly, a lot crazy. So then we have this one of my favorite examples. See if I can get this one right. Let's see if I can demo. Oh, I don't have the window up. Let's pull up a Ruby window. Can we see that? Yeah, okay. Now I'm going to rely on you for pair programming here because I can't see properly what I'm doing. That's the pretty printer, so I need that package. What else do I need? I need to get myself a copy of the... Huh? Oh, yeah, no, that's fine. I've just realized I'm not going to type out that expression myself. I'm going to swipe it from the slide. A bit of copy and paste. Okay, let's get the focus back. And, right, so let's create a function, f, that takes an argument n. And then we'll put 1 multiply it by n, so 1 is a string. Then we will mismatch that with the expression, and then we will be done. Now, what we'd like to do is pretty print the output. Let's transform that lot. Take an argument and reveal and yield a set of strings. So we're going to map the numbers 1 to 20 over an application of this function. Yeah, I think that's about right. I think that should do it. Right, so what does that do? 1 maps to false, 2 maps to true, 3 maps to true, 4 maps to false, 5 maps to true, 6 maps to false, 7 maps to true. What's it doing? Prime numbers, yes. This is one of the least efficient ways you can ever calculate a prime number or determine whether something is a prime number. It relies on a backtracking property, not true of all regular expression engines, but it's true of most of the Unix ones. It doesn't work, you can't necessarily rely on this for Java, but for Perl and Ruby, yes. And so this actually tries to determine whether or not it can match multiples of a sub-expression. Because if it can match multiples of a sub-expression, it means that it's divisible and therefore not a prime. So if it can't match it, it's a prime. How insane is that? Again, not something you can necessarily use at work, but it does show that although it's a fairly crazy regex, it's not very big. This actually allows you to calculate primes. How insane is that? So stuff you can do with a shell, it turns out, is enormous. There's a lot of fun to be had with this. This is a one-line web server. I mean, it's a very long line, and it does use tools, but it does show the compositional power of using the right tools, and it does deal with the only two error status codes you ever care about, 200 and 404. This is a one-liner from a guy called Alexei Sveshnikov, and I've seen longer versions. Now, obviously, this is not recommended. Don't immediately go back on Monday to work and say, that's it, we're throwing out Apache, we're throwing out everything. We are just going to go with this. It's light, it's lean, it's totally insecure. But again, this is fun, but it does show you that every complex idea that is successful typically has this essence of simplicity to it. You can distill it down. And this is very much the way with something like Unix and a lot of Unix stuff. This is a book. This has some really cool code in it, because this contains the Unix 6th edition source code. It's known as the Lyons book, after John Lyons, an Australian computer science professor, who in the 1970s wished to teach a course on operating system design. But what he was lacking was an operating system that he could talk about. Around that time, Unix was made available, and he was able to, what he did is he wrote this set of notes that was basically included all of the source code of the Unix kernel, a complete introduction to operating systems and the C language. And whilst we might look back on this and say, well, you know, some of the code style there is not great, from a modern perspective, we might question it. At the same time, it's worth pointing out that this is 10,000 lines of code. You get a whole operating system. I've seen classes that make 10,000 lines look small. Yeah? We call that other stuff enterprise code. So next time somebody shows you something and says, oh, look, this is real code, this is real stuff, it's 50,000 lines long, you need to think in yourself, that's 5 operating systems. Does it do that much? And the answer, I'm reckoning, is probably no. Okay? So it turns out there's a certain elegance, and there's this, one of the early papers on Unix, early 70s, the late Dennis Ritchie and Ken Thompson made this observation. There have always been fairly severe size constraints on the Unix operating system. Given the partially antagonistic desires for reasonable efficiency and expressive power, the size constraint has encouraged not only economy, but a certain elegance of design. This goes back to why many of the examples that I think of as being very cool are often very compact, very small, very light. There's something about them that teaches us how to distill down an idea. And sometimes we wouldn't end up with something quite so minimal or quite so effective and expressive if we had not been given the constraints to work within. Constraints can be annoying, but they can also be surprisingly freeing. So, observations on this, going back to the deeper history of some of this stuff. One of the interesting points of deep history is the Unix pipe system. Doug McElroy actually came up with it in 1964. There it is, wait a minute. He makes a number of things about I/O files and interaction. But let me think. We should have more ways of coupling programs, like a garden hose. You screw in another segment. He had the metaphor in his mind of being able to pipe data, textual data, flowing it through like a hose and connecting parts. This was the vision. It was not properly realized until much later. So McElroy got around to sketching out how to do the data processing. So now we're talking about 1970, 1971. By connecting together cascades of processes. And he was looking for the notation. It's funny, but it turns out sometimes that notation is the hardest thing to get around. The Nobel physicist Richard Feynman once described the history of mathematics as the history of notation. Finding a better way of expressing, making convenient a complex idea in a simple form so that you can fit it in here. And so you can fit it on a whiteboard, well, blackboard. And so we can fit it on a page. We can fit it on a screen. And so finding the notation, well, over the period, McElroy tried all kinds of things. One day, turns out, he came up with this process, and Ken said, I'm going to do it. He was tired of hearing all this talk, and he just did it. And so finally, he put pipes into Unix. And as they observed, the next morning, we had this orgy of one-liners. Everybody had suddenly discovered this expressive potential. Now, the reason I'm going to rest on something like that is it turns out that the streaming system, the pipelining system, is effectively a simple but remarkably expressive functional programming model. So if you use the Unix command line, you are using a functional programming model. And it is elegant and it's simple, and if somebody had said in advance, this is what we're going to do, it's very unlikely people would have been excited by it. It's one of those things that you have to use it to see the power. Now, this is a very interesting observation from Jeff Atwood. And let's just see if I can get, I don't know what the Wi-Fi connection is like. Let's find out. Okay. There we go. Okay, so this is Fabrice Bellard's Linux running on JavaScript. And it is a fairly comprehensive, it's a very fast emulation, and it's a very reasonable emulation. I mean, it's got all the details. There we go. Oh, heck, it's got a C program. Okay, let's have a look. What else would you write? Hello world. Okay, so it's got an editor. Let me think. Where do we want to go with this? I feel like I want to punctuate that. There we go. Okay. Okay, and what do we want? Let's try that. It takes a little bit of time. Yeah. Slowest browser of them all, really, isn't it? Chrome. No. There we go. Right, good. And there you go, fantastic. For the Emacs heads out there. Now, if you want slow, this is slow, because we're already running 2 or 3 levels of operating system. You don't need to run another one on top. So the best thing to do with Emacs is Control-X, Control-C. There we go. We've returned to normality. Now, if you noticed, there was a DOS directory there, which is absolutely fascinating. So this actually runs, so we've actually got DOS. There's an assembler script. So let's just actually print that one out. So this is some assembler code. This has already been pre-compiled. Let me think. What have we got? Let me think. I want HPI. Let's try that. So, anybody recognize the number? So that's an assembler program running as a CPM, it's actually CPM assembler running in a DOS context under Linux over a JavaScript emulator within a Chrome browser, which is also running within an operating system that has a hardware abstraction layer of its own. It's like watching Inception. So, just to reinforce that, yes, any application that can be written in JavaScript will eventually be written in JavaScript. So, then we have kind of the close, because all of this is the little email, the little group announcement from Tim Berners-Lee. It just sort of modestly sort of says, you know, this is now available in alpha release. This is 1991. This is the beginning of the web outside CERN. Really, really interesting. And we owe an awful lot to this, in effect. And this code is, in that sense, very, very cool. Again, we can regard it as imperfect in a number of ways, and yet it reveals so much and caused so much more. So, on that, I'm going to close this by making the observation, Stephen King, the author, if you don't have the time to read, you don't have the time or the tools to write. This is why this stuff is interesting, because it is of intrinsic interest to our domain. It's not that it's necessarily code that you can use. It's far more profound than that. So, we'll close the conference, and I thought I'd change the emphasis here. Now it's the end of the conference. There you go. Thank you very much.